Look at this page. It looks exactly like the Facebook login page. The browser even shows the lock icon and the address bar says facebook.com. So the browser believes we are connected to the real Facebook website. But what if I told you this page is actually hosted on my own machine? This is not Facebook's server, it is a fake website running locally. So the real question is, how did I make the browser trust facebook.com even though the traffic is being redirected to my own server? Let's see how this works. In the previous video, we explored how your browser decides whether a website is legitimate. We talked about the trust chain behind HTTPS and how your system verifies that the server you are talking to is actually who it claims to be. But what happens if someone tries to fake a trusted website? Today, we are going to simulate exactly that. We'll redirect a real domain to a fake server, generate our own certificate, and observe how the browser behaves when it encounters something that looks legitimate but it is not. Now, imagine you wake up in a room with your laptop exactly as you left it, no one touched it, but the router connected to the network is not yours and you have no reason to trust it. That means the router could potentially control the DNS responses your computer receives. Now, suppose you type facebook.com into your browser. You expect to reach Facebook's server, but what if the router sends a false DNS response? Instead of giving your computer Facebook's real IP address, it could point the domain to a completely different server, one controlled by an attacker. From the browser perspective, nothing looks unusual. The URL still says facebook.com. The page might even look identical to the real one, but behind the scene, your traffic is being redirected to a malicious server pretending to be Facebook. So the real question becomes, how does your browser detect that something is wrong?
Before we begin, this video shows a controlled lab simulation for educational purposes only. This demonstration was performed in a secure test environment to explain how browsers handle certificate validation, hostname matching, and HSTS protections. It is not intended for real-world use, impersonation, phishing, or abuse of any service or brand. Please do not attempt this outside of an isolated lab environment and only use systems and domains you own or are explicitly authorized to test.
For this demonstration, I didn't modify DNS on a router or interfere with the network infrastructure. Instead, I changed the DNS resolution locally on my machine. That means whenever my computer tries to resolve Facebook.com, instead of receiving Facebook's real IP address, it receives the IP address of the server that I control. In other words, my system now believes that Facebook.com is hosted on my own machine. At this point, we have recreated the scenario we described earlier, a domain name pointing to a malicious server. But there is still a problem for the attacker. When my fake server responds to a browser request, it must present a certificate. So I created one. The certificate's common name is facebook.com, which means the domain name technically matches what the browser expects. However, matching the domain name is only one part of the verification process. The browser also checks who signed the certificate. It then checks who signed that certificate and continues working up the chain of signatures until it eventually reaches a root certificate that exists in the system trust store. This process is known as certificate trust chain. In my case, the certificate I generated ultimately chains up to a root certificate that I created myself. That root certificate does not exist in the trusted store of the operating system of the browser. So, when the browser tries to verify the chain, it reaches a dead end. The root cannot be found, and the browser immediately warns the user that the certificate is not trusted. This is exactly the behavior we want. When I visit the server using its IP address or another domain name, the browser gives me the option to accept the risk and continue. But when I try to access it using the real domain name, the browser shows an HSTS error, and this warning cannot be ignored. Normally, this happens when the server sends an HTTP header telling the browser that if there is any security problem with the connection, the browser should not allow the user to continue. However, browsers also enforce this behavior by default for well-known domains. They already know that websites like Facebook should always have a valid and trusted certificate. So, if the browser suddenly detects a certificate problem for one of these domains, it assumes that something suspicious or risky is happening, and it blocks access completely. There are also two fundamental reasons why I couldn't create a legitimate certificate for Facebook.com. First, I do not possess the private key of any trusted certificate authority, which means I cannot forge a certificate that changes to real certificate authority. Second, even if I tried to request a certificate from a legitimate authority, they would verify that I actually control the domain name Facebook.com. Since I don't, the request will be rejected. So instead, I created my own root certificate authority and signed everything myself. I built a complete certificate chain that is technically valid but ultimately anchored to a root that no system trusts. But now, let's see something interesting. If I manually add my fake root certificate into the system's trusted root certificate store, the situation changes completely. Suddenly, the browser can work the chain successfully, the root is found, the signature is valid, and the connection is accepted. The browser now believes that everything is legitimate. The domain says facebook.com, the certificate chains appear valid, and there are no warnings. But in reality, the browser is communicating entirely with a fake server. Now, something interesting happens. When I try to enter my credentials, the browser even suggests my saved passwords because it believes this is the legitimate Facebook website. From the browser's perspective, the domain name matches, so it assumes this is the same site where those credentials were originally saved. And this reveals the most important lesson in HTTPS trust model. The entire system of certificate verification, the signatures, the chain validation, the cryptography, ultimately depends on the list of trusted root certificates installed on your system. That list defines which authorities your computer trusts to vouch for the identity of websites. If an attacker manages to insert their own root certificate into that trust store, they gain the ability to create certificates for any domain they want. At that point, they can intercept and impersonate secure connections without triggering any warnings because the browser believes that chain is legitimate. In the next video, we will talk about how DevOps engineers generate manually certifications and build a trust chain locally. See you then. Bye bye.